Okay, so Peter just gave a really great talk about EuroEXA from the hardware point of view. So now it's the second talk about EuroEXA and also one of the feed-in projects, which was ExaNoDe that Peter mentioned in the previous presentation. But this time the focus is on the software side. So it's going to be a very different way of portraying the project. We have 14 full-scale applications that are being used in EuroEXA, which are coming from 10 different partners. We also have the full software stack from the OS, runtime system, accelerated libraries, resource management. The work on this started in ExaNoDe and is being continued in EuroEXA, and is used basically to demonstrate the machine that we're building, to evaluate the machine, and also to drive the co-design, which Peter mentioned in the previous talk. So briefly, I'm Paul Carpenter. I'm at the Barcelona Supercomputing Center. We've been part of this exercise since EuroServer, which was 2 years before ExaNoDe. And I'm leading the applications work package in EuroEXA and also the software side of that project and the programming environment and system software work package in ExaNoDe. So I will repeat some of the kind of top level slides or content on EuroEXA just to make it self-contained, also for the benefit of the people watching the video. So we're co-designing and building and demonstrating a test bed with a target of 1 petaflop equivalent performance in an operational environment. So this is more than just a prototype in the lab. We're building on technologies that we first started working on in EuroServer and then fed into ExaNoDe, ExaNest, and EcoScale. So one of these is what we called UniMem. So this came first from EuroEXA and is a global shared address space with coherence islands, which is built on top of the Amber bus and the ARM interconnects. What we're doing that's really new, I think, from my perspective in EuroEXA, is that we're using these full-scale applications. So in ExaNoDe, we did some of this, but we used mini apps, so at the level of benchmarks. Now we've got a lot of partners that really have the expertise and really want to see it working on the production applications. And on the co-design side, I'll talk more about how we've tried to balance the performance, resources, and the application needs. So this is the slide that we just saw from Peter. I added EuroServer in because even though it's not HPC, it's part of the same progression. So we started in 2013 with the 3.5-year EuroServer project, which had many of the core partners. The focus was on microservers, in fact, instead of HPC, but there's some commonalities in the technologies. And then in 2015, of the 14 or so HPC projects that were started at that time, 3 of them were these overlapping projects related to what we're talking about now. So ExaNoDe is concentrating on the node architecture, so it brings MCM integration, it brings runtime systems and things in the node. EcoScale is FPGA offloading with an OpenCL programming model, and ExaNest, the title comes from the fact that it focuses on the networking and the storage.
Just a quick question. How does this relate to EPI?
This was before EPI, right? This is, I would say it's a separate initiative with different partners. We would like what we're doing to be compatible with the EPI approach, and we would But I shouldn't say.
I mean, would you
more.
say that they're focused strictly on the processor and you're looking at the systems? Or no?
I would rather not talk for EPI.
Okay.
Right. I can talk for us because we're focusing on the system and the applications to use the system.
So is this competitive with EPI? Or
No,
am I pushing
complementary.
too-
Complementary.
Okay.
So this is a picture of the partnership. So since I'm from the application side, I'd like to point out that many of the partners here are in this EuroEXA project because of the applications. So we have one of the commercial partners, Synalexis, in life science. We have astrophysics from Italy, IMEC application, ECMWF, nuclear physics in Italy. This is again life science application. IMEC has applications. BSc has several things, but including applications. And of the supporters, many of these told us they're collaborators of our application partners and really want to see the performance delivered for real applications that they're interested in. So when we set up the consortium, we were really trying to make sure that we could build something that's useful, not just make some fun hardware and kind of get the money. So we already saw this. This was the project call, 3.5 years, 20 million budget, roughly half hardware and software. Lot of budget goes into hardware, but then a lot of PMs and resources go into the application development and the runtime development and everything else on the software side. So very quickly, the first test bed, which Peter also mentioned, is based on technology from Forth. It's actually the quad FPGA daughter board. It's an old slide that says censored. I just noticed that this morning. It's a Xilinx UltraScale Plus FPGA, which brings each of them 4 A53s, FPGA accelerator, and the other hardware stuff you would expect on a board. The blades, Peter also mentioned, we have 16 cards in a blade, in a half-depth chassis, sort of power consumption, the innovative liquid cooling, low voltage DC power, and the hot water out, which is more the subject of Peter's talk. So we started the beginning of the project with testbed 1, which is based on the QFTB. Testbed 2 is a larger scale, was also supposed to be based on the QFTB. I will talk later about the co-design Triumph, which has changed the direction that we're going in, I think, in a very positive way. And then at the end of the project, we have the final testbed, which brings some new node and processor technologies and builds on top of that. And that's basically the third year of the project. So that's a quick overview of EuroEXA, which is the big project, 20 million, that started last year. This is ExaNoDe. So this one started in 2015. It's a smaller project, less than 10 million. As I said, it's concentrating on the node. We can see many of the same partners. BSC's in this one, CEA is coordinating it, and many of these are on the runtime system and also on the silicon integration side. So in ExaNoDe, we have hardware integration, die stacking with active interposer. So this is a CEA technology to basically put multiple chiplets into one device with an interposer. The architecture is based on ARMv8, with the scale-out architecture referring to the UniMem approach that I spoke to before. FPGA is available in the node. We started some of the programming model support for the FPGA in an early way, and software stack, as I said before, mini apps to demonstrate. It's focusing on the node, so we're not scaling up to exascale or something. We have 4 runtime systems, MPI or communication libraries, MPI and GPI, the OMPs, task-based runtime system. Our programming model, an OpenStream, is also an OpenMP-based programming model. We have power and thermal management from ETHZ, work on virtualization in KVM, so checkpointing and remoting of the accelerator, and the OS work to support the Uniman hardware, bring it up into user space. And we build an integrated prototype here, demonstrating the multi-chip module here, demonstrating some of the achievements on the software side. And this is a picture of the board that we're working with. So we have 2 MCMs, each with 2 FPGA bare dies inside, and another chiplet used primarily to validate the integration technology. And this is on a board with the power supply and so on. So that's a quick overview of the 2 projects. So now the question is, why do we put so much emphasis on applications in the EuroEXA project? And this is a very simple way to kind of demonstrate the idea. So you build a exaflop, or so many flop machine. That's your theoretical performance. You run LIMPAC or DGM, dense linear algebra. You get, if you do it properly, you get maybe 80% on the CPU. That's really good. But then you look at you look at benchmarks, for instance, like in ExaNoDe and mini apps, and you start to see disappointing numbers. And you run graph algorithms, and you run production HPC applications, and you get a few percent. And one example here, for instance, is the Taihu Lite from China. That's 93 petaflops and 6 gigaflops per watt. So excellent. Until you try running HPCG and you get 0.3% of that. So that's really what we want to avoid doing. We want to build something that's not a stunt machine that's great for LIMPAC, that gets great Green 500, but we want to build something that can actually demonstrate real performance on applications. And I think that is linked to the question about what you mean by exaflop also, or exascale. It's not, this is exa, it's that you built a machine that's maybe 100 times as fast as a 10 petaflop machine for real applications, broadly, that sort of thing, rather than counting the number of Macs that you've got in the machine. So here's a picture of the applications that we've got. Very quickly, you can see there's a balance. We have some sort of physics or energy or astrophysics, or some other ones. This one here, that one, and we have sort of material science, and we have weather and climate, weather climates, another one there. We have some neural simulating, and here we have reverse time migration, and engineering, other physics. So we tried to get a balance of applications across important domains that will need exascale in future. We also tried to get some sort of balance across different requirements of applications. So these, and this is very simplistic of course, but these are the ones where the developers told us they're primarily compute bound. One part of LBM, these other applications, these guys are memory bandwidth bound, these guys are IOP bound. So we tried to get some balance so that we're not just looking at one kind of application. And then why these 14 applications? Well, partly it's not just the applications, but it's the partners that we bring in. And here I think we've got 10 very strong European partners by bringing these applications. We cover 3 important application domains: climate and weather, physics, energy, life science and bioinformatics. These seem to be domains that will require exascale style computing in the future. We also got some applications that were part of the Price UEAB suite. So these are applications that are used by the large supercomputing centers in their procurement process. So these are important in basically validating the machines that they buy. And while it doesn't relate to the title, but we use them as a target to port to the machine, to demonstrate that the machine is doing what we said it would do, evaluate the machine after we've built it, extrapolate up to larger machines through a sort of simulation approach, and for co-design. So for co-design, we also took a kind of global look at the consortium and made sure that we have all the people in the room across the whole stack. So we have, as I showed before, a good number of very strong application experts. We have system software, programming environment experts. We have the system architecture, the hardware side. We also have industrial partners who can bring the kind of commercial aspect to this endeavor. And we bring applications here, we may need to adjust them. We have some hardware parameters and trade-offs. We may need to rethink it. And well, I'll talk more about the process in a future slide. So this is, I guess, how we approached it. So the first thing we did, and I'm maybe being a bit frank here, is to ask ourselves whether we really were going to do co-design. Because I think people with kind of experience maybe can be a little skeptical. I think that's because co-design is actually very challenging. It's very challenging, full stop. It's also, I think, very difficult to do in the context of a 3 or 3.5 year project, because realistically speaking, you have to start doing development at the beginning of the project in order to deliver something and have it evaluated by the end of your project. So there's not a lot of time to sit around and kind of do blank paper analysis and proper co-design. It's a challenging environment to do this kind of exercise. But we thought it was something that we really should do. We didn't want to do kind of a box ticking exercise and just pretend to do co-design. But there was also a question about how we should do it. And the approach that we took started by the hardware guys telling us what were the open parameters. And this maybe you could say is kind of compromising. We should have started off as equals like our picture and started from the application down. But that also relates to the short time frame that we had. We made a commitment that we were going to build a machine of a certain size. So realistically speaking, there's no point going off in random tangents. So we started with a very good, very constructive input from the hardware side about what were the true trade-offs there. We formed a co-design working group. I headed that working group, but I wasn't the biggest expert there. We had conference calls, workshop. We are just putting the final touches on a recommendations document, which will also, of course, be a deliverable to the commission. And I tried to separate, there's a fine line, but I tried to separate the recommendations that came from this process from what the project actually does. Because I probably should have said when I was talking about co-design, but there's also the commercial realities. And it's all very good to say what's perfect for this HPC project is another thing to say what fits in with commercial plans and so on. So this we put separate, partly as a kind of risk management exercise. How am I doing on time? Actually, maybe I'm
close, I think.
okay, not too bad. Not too bad. I think we're a bit ahead of time. So we also had a question about, so we have some trade-offs to look at. How are we actually going to do these trade-offs, right? We can do some simulation with hardware simulators. We can use analytical models. We can run on another machine and maybe do some estimates of how it translates to another machine. We can do a state-of-the-art analysis and more or less copy what the other guys do, and kind of maybe not the most favorable way, but that is also an important thing to do. And of course, we can't do everything perfectly because we can't have a simulator of the whole thing with a full exascale application and all the system software and everything. We have to be pragmatic about what we're actually going to do. So in the end, I'm going to run through 3 examples that more or less show one case we sort of looked at state of the art, another case we did some simulations, another case we looked at experience from other partners and the progress so far on the application side. So one thing we used was previous experience from the ExaNoDe project. And there's a very good public deliverable from ExaNoDe that does a kind of state-of-the-art analysis on the sustained versus theoretical flops of other existing systems or platforms so that we can position ourselves against that. And I won't go into a lot of detail here because I have a lot of time, but this was a kind of roofline analysis, which I guess you guys have all seen with lots of different machines. I'm not quite sure where ExaNoDe fits on there because we haven't drawn it yet, but this is one thing we did. So let's look at what everyone else is doing, see an enormous range in terms of memory bandwidth and flops, but we can position ourselves against that. Another thing which we looked at, and this is without giving details on the quantitative side because obviously I can't, is do you want more L2 cache or do you want more cores? So do you want more cores? Yes, please. Do you want more cache? Yes, please. But what's the trade-off between them? Do you want something heterogeneous? No, don't give me that. I don't want these 4 cores with lots of, well, maybe I've drawn it wrong, right? I don't know, but some combination where you have different sizes of caches in the system. So this is one where we used some simulation, and we've got a good set of conclusions that are being used by the hardware side. And this was based on applications that were contributed from the application partners. We have some other parameters. Again, I can't go into details, but just to give an idea of what we were looking at, we have a partner that's doing hardware memory compression. Suffice to say, they had some design parameters and trade-offs, and we gave some input onto that. Clearly, I can't say what this actually relates to. Questions on, again, Unimem parameters on the implementation side, some of the interfaces, whether you want fast or slow or high latency or so on. And network topology, we will look at in the second year of the project. So we tried to concentrate on the stuff where we have to make the decision early on. And the network we do have to do, but there's a bit less time pressure than the others. So this is then the co-design triumph, I would say, because this was somewhat unexpected. It was something where in the co-design workshop we started talking about, or at least one of the partners started the discussion about the whether we were going with the right approach with the QFTB, and whether we should be using 4 small FPGAs or whether we should be using one of these and a bigger FPGA. And we had a discussion. We involved the application expertise, and we came down on going this way. Oops. And briefly, the reasons are this gives you more FPGA resources, higher I/O bandwidth and memory bandwidth. There's already been applications demonstrated on this larger FPGA that haven't been demonstrated on the smaller FPGA. The smaller FPGA, because it's been divided into smaller FPGAs, has more of the compute FPGA used for the interconnect already. The application has to be divided up into smaller parts, and it was, I think we did conclude a 4 times roughly performance improvement from going this way. So that more or less finishes the co-design, just on a kind of quick run through. So as I said, there were some real parameters that we really looked at, and we made a real change in the prototype specification based on this exercise. So
real code design is very difficult.
I know.
It's disruptive, right? When you're continually doing that code design, continually considering it, it's quite a disruptive activity.
Because you have to.
It can enable continual specification creep. So the thing that I think we managed to get right is that we put co-design so that disruption occurs in bursts, and that if disruption or change becomes a good point for convenience, it becomes convenient to consider change at any point, and it's kind of flagged. And at that time, the disruption of co-design is enabled. That's kind of the way it seems to work. Whereas I think if you had a continuous co-design process that was constantly outputting things, you'd end up with just crazy specification creep.
Yes. And I think you are right to use the word disruptive, because it's one thing to change a chip on a board, but then we do have to make sure that the corresponding work is done to make sure that it works. There will be some rethinking of some of the work that's been done on the application side. So at some point, it's not just a technical decision, but it's also a planning decision. And it's very important to do that in the right way. So now I make a context switch to the software stack. And I guess the message of this slide is that we have a lot of stuff going on the software side. I probably can read it all out. We have storage, we have BGFS, we have stuff in the kernel. So for the memory compression hardware, I said obviously needs kernel support. The Unimem needs kernel support. New work on the network side needs kernel support. We have accelerated libraries that are being done for sparse computations and so on, work on the tools side, tracing and so on, work in the batch scheduler, for instance, for the resource management, exploiting capabilities of Unimem and sharing memory capacity, runtimes, a lot of work on MPI. We have continuing the work with OpenCL, offloading to FPGA from EcoScale. We have PGAS from Fraunhofer, so this is GPI, Manchester's OpenStream. We have BSC's OMPs on FPGA and distributed memory, Maxilla, and so on. So the thing is, I don't have enough time to go through all of it. So I'll just give some highlights of some of the things that we're doing, maybe slightly biased because I might talk about things that I'm more familiar with. So on the programming environment, one thing we tried to do was abstract the important or the innovative capabilities of the hardware. So we have Unimem, which has a very specific API for Unimem. And we have FPGA acceleration, which is very difficult to use directly without help from the applications. So we really didn't want the application guys to go writing specific Unimem code. For instance, they should be using MPI or GPI or something. And we want basically the programming models and the communication libraries to target a portable layer. So a programming model or an API, maybe one of these, and to move much of the optimization of the specific aspects of EuroEXA into runtime systems. So very quickly on the programming environment side, Peter already mentioned end of Moore's law. I see that as enabling a lot of very interesting work, more kind of these things, specialization that we see from FPGAs and so on, basically as a route to get more performance. It's not just keep making the CPUs faster and go on that road. It's now do more interesting things, deep memory hierarchies, all these accelerators, variability, complicated data placement, and all these sort of things, making it very difficult to target on the application side. Because I think maybe one thing that some of us don't realize unless we talk to the application guys is that they're scientists or they're engineers, and they don't really want to spend all their time optimizing for a machine. They want to solve their science problem, which maybe means publishing in Science or Nature, or maybe means bringing out a project using engineering simulations. So this, maybe for us, some of this is, or for me, some of this is good fun, and something I really want to kind of get worked into. But this is not something that the application guys really want to be working on. So this is basically the motivation for more intelligence in the programming environment. And one thing we did early in the project, and maybe this is slightly out of date now, something we did in the second or third month of the project, is we got together all the application guys and all the programming environment guys, and we had the programming environment guys basically present their programming environments. We had the application guys talk about their main problems, and we tried to kind of have some first estimation of which programming environments seem promising to help which applications. And this is something that we've built on in the project, especially for the FPGA support, but also for the OpenStream. There's a few more in here, and GPI and the other programming environments. So we found this a very productive way to work. So one of the programming models that we have is OMPS. So this is a result of 10 years of investment. BSC is more or less an advanced version of OpenMP. So we kind of propose new extensions, the tasks and the task dependencies that were eventually added to the OpenMP standard came out of work at BSC. So we tried to advance the state of the art and then try to get this into future standards, and then it can be adopted by the application guys. So it's task-based program. There's a single, at least for the application developer, there's a single address space and namespace for the data, and it happens to execute in parallel because the runtime system computes the dependencies and executes the tasks in parallel. And it runs on SMPs, GPUs, clusters, and even FPGAs. So there's now a back end that allows you to write the tasks, which are basically compatible with the SMP or CPU tasks using high-level synthesis, and all the difficult stuff in terms of kernel drivers and data movement in and out of the FPGA and hardware interfaces and so on are handled by the runtime system. And this is something that many of the application guys are working with to try to port their applications to use the FPGA support. This, maybe I'll move quickly, is basically normal compilation flow, which includes the Vivado HLS tools as part of it to generate a bit stream, and then you get an executable and a bit stream that run together. At compilation time, you have to make some decisions, like the number of instances of various tasks to burn into the FPGA bit stream. And I think these are old results, but I guess the point from this is that the runtime system runs tasks on both the FPGA and across the cores. And by running on both, you get, maybe just on the FPGA you get this, but you also get a performance boost from running on the cores as well. Another variant that we have runs on distributed memory. So this is more or less extending OpenMP, which is shared memory programming model, to offload tasks across nodes on the machine. So it can either be an alternative to MPI, or it can be a complement to MPI. This is something that we're targeting with several of the applications in the project. Here, all the processors have the same virtual memory layout, which means that tasks can be offloaded across the nodes, and pointer data structures and graphs and so on can be easily dealt with without having to translate the pointers from one processor's address space to another processor's address space. So this was an important decision that we made at the beginning of this project. And at the moment, in terms of distributed data structures, we're focusing on multi-dimensional arrays distributed across the machine, and we're adding support for graphs in another project. So I'm coming to the end of the talk. One last runtime system that we have is MPI. So there's a lot of work on the full Unimem optimized MPI, which is based on MPitch and delivers full MPI 3.1 functionality while optimizing the communication using RDMA on maybe, how many minutes? Okay. I think I have one more slide after this one, so I can deal with it. So yes, this is something that we're supporting in the project. We have the full MPI, and we also have a more experimental version that's being used more for the co-design aspects. Maybe I jump over this if I'm running out of time. We did some application requirements, porting mostly to FPGAs. It's a very steep learning curve, I would say. It's very, and I think, speaking honestly, it's going to be very challenging to expect full performance by the end of the project. I think we should be very pleased with ourselves if we have made very solid progress on some of the applications, because I think to get ourselves into a position where applications can really exploit FPGAs, I think is more like 10 years than 3 years. So, but I think we need to do this work, and I think we will, at the end of this project, have made quite some progress on many of these applications. So conclusions and visions, we're building this machine. We have vision towards basically contributing to the exascale vision in Europe. We're running the full applications. We've done co-design, which has had a lot of success on the change of the FPGA and also the design choices. And we're developing the full programming stack and porting the applications to this architecture. And that's it.